Okay, so today's lecture is about data compression. Okay, so what is data compression? Data compression is the objective of data compression. Okay, is that we want to be efficient. As I said, that we want to use the resource of the communication system as little as possible, use the bandwidth as little as possible, so that we can send the data from many users at the same time. Okay, so we want to send as few bits as possible. Now, in order to know how we can change from 1,000 bits, okay, to 800 bits or to 500 bits and transmit, okay, we have to understand that data and information are not the same. Information is abstract, okay, of what we want to send, but data are the means that we use to transfer the information. So information is abstract, but data is something discrete, something that we can touch, okay, we can use, okay, this is a word, this is alphabet A, this is alphabet D, something like this. So what is on the sheet right now, okay, the alphabet or the words that you are seeing right now, they are data. But what I'm trying to give to you, okay, is the information. There are two techniques, okay, two main categories of the data compressions, okay. The first one is lossless data compression. The second one is lossy data compression. The lossless data compression is to be able to reconstruct exactly, okay. So if you send, if you have original data 1,000 bit and you compress it to 500 bit, you have to be able to reconstruct the original 1,000 bit back exactly, okay, from the compressed data, okay. So for example, it's the compressed text files, okay, such as the .zip or .zip or .rar. Zip file or .rar, okay. These are compressed text file, okay. Okay, for the lossy data compression, okay. In some application, you cannot do the lossless data compression, and sometimes it's not worth it to do the lossless data compression, okay. So you may select the lossy data compression option instead, okay. So in some, for example, if it's an image, it's okay to lose some information, okay. It doesn't have to be exactly as what we see in real life, okay. The picture, they have to, for example, we can use like just 255 colors, or which is not the real one, okay, because the real thing that we are seeing, there's like infinite possible color, like the sky, something like that. But it's okay, okay, because we can still give the user, okay, at the end, okay, the destination, to understand what we are trying to send to them, okay. So the objective for the lossy data compression is that we want to satisfy some fidelity criteria, okay, that the user will need. So it has to be, the picture has to be like nice enough. If you want it to expand it into big pictures, okay, to post it on the wall, you have to use a very high resolution, okay. Maybe 10 megapixel, something, 20 megapixel. But if you want it to post your profile, okay, a small picture in your website or in the internet, you can use very low, much lower resolution, okay, because just to see, okay, who is this. But if you expand it, you can see that it's not, the picture will be, the pixel will be broken, okay, it's not clear. So this is example of lossy, is the sample and quantized sound or pictorial information. For the lossless, okay, now let's look at the techniques, lossless techniques, okay. The first one is length coding for text data, okay. The code will present the value and the number of the same symbols. in succession. Now let's look at an example. Untitled coding. This one is for text. Okay. For example, I am sending this data. Okay, so what do we have? We have 10, 17, 23. Okay, so we have 23 symbols or alphabet that you want to send. Okay, but if I use so this is original. Okay, this is original. Okay, now if I use untitled coding to compress. Okay, so the compressed data will be like this. 6A, 3B, 7C, 7A. Now, so you send this, okay, instead of this one. So how many alphabet or how many symbols are you using? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8 symbols. So you compress from 23 symbols to 8 symbols. Okay. Now, at the receiver, if the receiver saw this and it have agreed with the sender, okay, that this is the number of the symbols that follow, okay, of how many that A will repeat. So at the decompression, when you decompress, okay, 6A equal to 1 A, okay, 3B equal to B, 7C, okay, so you can do like this. And this is exactly the same as the original, okay, similar to, exactly the same as the original, okay, when you decompress. This is called lossless, okay, data compression. Now the second technique is called Halfmann coding. Okay, Halfmann coding is follow the name of Halfmann. Okay, he's the one who create these coding techniques. Okay, Halfmann coding use unequal probabilities of symbols in a sequence to reduce the number of bits to represent the sequence. So some sequence may occur, but some symbols may occur more frequent than other symbols. Okay. So we will encode it, the one that occur frequently, okay? More frequent, we will code it with shorter code word, okay? Shorter, less number of bits. If the symbols is rarely happened, we will encode it with longer bit sequence, okay? The Halfmann coding is optimum, okay? It's called optimum prefix code, because it provides a maximum expected length code, which means that it's the code that has the expected length of the code, or the average, okay, length of the code is minimum if you know the probability distribution of that symbols. Okay, for example, if you have A, B, C, D as a symbol, and the probability that it is occur is 1/2, 1/4, 1/8, and 1/8, okay, respectively. Then if you do the two-bit code, okay, this is the normal one, or the usual one, that the easiest one that we can do, okay. So A, B is 4 different cases, okay. So we can use 2 bits to represent. A can be 0, 0, B is 0, 1, C is 1, 0, and D is 1, 1. But if you do Halfmann code, you can see that the length of the code are not the same. A use only 1 bit, B use 2 bits, okay? C and D use 3 bits. Okay, this is the method, okay, of how to find the Halfmann code when you have the probability distribution of a set of symbols. Okay, first you order the symbols based on the probability Two, we will pair two symbols with the least probability together. I will show you an example in a little bit, okay? Then you repeat number 2 until all symbols are included. Okay. 4, you assign 0 and 1 value to the branch of the tree. Okay, you will see a tree in a minute. 5, read the value from the root to each leaf to get the Halfmann code. Okay, so let's look at an example. For this example 1, as in the sheet, okay, you have symbol A, B, C, D with probability of 1/2, 1/4, 1/8, and 1/8. So it's already ordered, okay? So I will put it here like this. It's already ordered for the first one that order the symbols based on the probability, okay? So A, B, C, D is already ordered. So this is 1/2, 1/4, 1/8, and 1/8, okay? Now, pair two symbols with the least, okay? Pair two symbols with the least probabilities together. So which ones are the least probability? So this one, okay? This one are paired together to get 1/4. Okay, so you add them, add the probability. So this is 1/4. Okay, then repeat number 2. Okay, repeat number 2. Okay, until all symbols are included. Okay, so pair. Okay, now 1/2, 1/4, 1/4. Which ones are the least, two least probabilities? So this and this. So you add them together, you have 1/2. Then you repeat it, you add together, you get 1. Okay. This is a tree. This is a tree. Okay? And this is the root of a tree. Okay? And these are the branch. So these are the branch of the tree. And these are the leaf of the tree, okay? This leaf. Okay? Now, we assign the next one, assign 0 and 1 value to the branch of the tree, okay? So we assign, if I use this one as left is 0, right is 1. So I put here 0, 1, 0, 1, 0, 1. Okay. And then read the values from the root to each leaf to get the Halfmann code. So I read it. This is my root. Okay, this is my root. To the leaf, read it like this. To the leaf, this is the leaf. So I saw 0 here. I put 0 here. Okay. Then this one is 1, 0, 1, 0. Okay, this one is 1, 1, 0. So 1, 1, 0. Okay, this one is read like this 1, 1, 1. So this is the code that I found. A equal to 0, B is 1, 0, C is 1, 1, 0, D is 1, 1, 1. Now let's look at the answer here. See, it's the same. Okay, now we have to find the average bit per symbols for the Halfmann coding because we say that it's the optimum code. Okay, the expected length code, the expected length of Halfmann code is minimum. So now let's find the average length code. Okay, expected length code and average code length of the code is the same. So what is this? This is you can see that when you want to find the average, you find the length. Okay, the length multiplied by the probabilities that it occurs. So the length is 1 multiply probability of A. Symbol A has the length is 1. Okay, of 1. Probability is 1/2. So you 1 multiplied by 1/2 plus 2. 2 is B. B has a length of 2. Has the property of 1/4. So it's multiplied by 1/4. And C and D has a length of 3. Okay, so length of 3 has a probability of 1/8 plus 1/8. So 1/8 plus 1/8 plus 1/8 is 1/4. Okay, so you have 3 multiplied by 1/4. So you add them together, you got 7 over 4, which is 1.75 bit per symbols. Okay, this is lower than the average of 2 bit per symbols for the 2-bit code. Because for the 2-bit code, every one of the symbol has 2 bit length. Okay, so average is 2 bit. So you see that this one is save, save the number of bits that you want to send. Now let's look at another example. Okay, so from this example, if we want to transmit, okay, suppose I want to transmit A, D, C, C, A, B, okay, I want to transmit this. I want to transmit this. So what do I actually have to transmit? A is 0, B, D is 1, 1, 1, C is 1, 1, 0, C is 1, 1, 0, A is 0, B is 1, 0. Okay, so I transmit this. Suppose I have received the same thing. Okay, if I have received the same thing, there is no error here. Okay, suppose I got the same thing as this. Okay, how can the receiver know what is the code word? What is the alphabet that reference how to interpret this to be the symbols? Okay, the decoder has to also, the receiver has also to know this, that A is 0, B is 1, 0, C is 1, 1, 0, and D is 1, 1, 1. The receiver has to know this. Okay, have to agree upon this. So when it receives this, when it sees 0 here, what can be 0? Okay, start with 0 is only A. Okay, only symbol A can be 0. So this is A. 1, what can be 1? It can be B, C, D. Okay, so look at the next bit. The next bit is 1, 1. So it cannot be B. Okay, it can be C or D. Now let's look at the next bit. Next bit is 1. So it has to be D. Look at 1 again. 1, 1 and 1, 1, 0 is C. Okay, this is 1, 1, 0 again, C. 0 has to be A. 1, 1, 0 has to be B. Okay, so this is uniquely decodable. Okay, which means that there is only one way to decode this into the symbols. So there will be no problems in confusing, okay, of what is the symbols. And it's also instantaneously decodable. Okay, this is the probability of the property of Halfmann code. Okay, Instantaneously decodable means that when you receive the bit, okay, the complete bit for that symbol you can decode immediately. Suppose you got this 0 here, you can decode that is A. You got the next bit, you cannot decode, okay, because it's not complete. You get the next bit, you cannot decode. When you get the complete for D, okay, you can decode that it is D. This is called instantaneously decodable code. Okay. Now, so that is Halfmann. The next topic is the encode string of symbols by frequency of occurrence. This is similar to Halfmann code. However, this is kind of used with the English language. Okay. For example, the Morse code. Okay, we use the Morse code. We use like the long, like a line and a dot. So Morse code we use line and a dot. It will be something like this, or dot, dot, something like this. Okay, so this is Morse code. Okay, and you can check what is the alphabet for that, A, B, C, D, something like that. Okay, now the alphabet that is occur most often is E. Okay, most often is E. So E will be the shortest. Okay. The shortest, it will be only one symbol, okay? We can check, actually we can check the Morse code here. If you want, you can check what is the Morse code. Okay, see? You can see that, okay, so this is the Morse code. You can see that E is 1 dot, okay? And what is the longest? The longest is 4, okay? Length of 4. For example, Q is dash, dash, dot, dash, something like this, okay? So Q happen less often, okay? Maybe rarely happened. E is short, the most frequent happened alphabet, and then T is also 1 dash. Okay, so you can see that T is also happen frequently. Okay, A is also happen frequently, so it's have only 2 symbols. Okay, dot and dash. Or you can use statistical dependency in a sequence, okay, to reduce the number of bits to represent the sequence. For example, if you know that Q is almost always followed by U, okay? If it's a Q in an alphabet, it's almost always a U, like queen, or Q, okay? So Q is almost always followed by U, okay? So if you want to reduce the number of symbols, you can send Q and then EUE, okay? And then when at the receiver know that if there is a Q, then you add receiver, add U by itself, okay? Because it's know that you have to add U at the follow the Q, okay? So this transmit. If you use a code that is, okay, this is what this is what I'm saying, okay? Q is almost always followed by U. Okay, the next techniques, okay, are categorized into lossy techniques, okay? The line coding is also lossy techniques, okay, both lossy and lossless. If it's a text, it's lossy. If it's sending text or alphabet, okay, like ABCD, okay, is lossless. But if it's an image, okay, it will be lossy. For example, if you have a picture, okay, suppose you have a picture like this, very basic picture, okay. Okay, now, when you want to transmit it, you have to quantize it into pixel. You have to put it into pixel like this. Okay. So you divide this into the picture into pixel. Okay, so this is run length for image. Okay, this is lossy. Okay, so if you look at this one is blue, 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 blue. Let's say this is white, white. Let's say this is also white, blue, white, white. And then blue, 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 okay? So what we do is that, for example, this maybe 10 blue, okay? 3 white, 10 blue, something like this, okay? And then maybe 5 red, okay? 10 blue, 20 blue, for example, 5 white, okay? So you can see that when you transmit this, okay, to the receiver, okay, so this is transmitted. Transmitter send this to the receiver. When receiver look at this, okay, it will look at 10 white, 10 blue, so blue, 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 okay, 10 of them, and then 3 white, 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 okay, so it put it in color like this, okay, and then it will reconstruct the pixel by pixel, okay, back into the picture. Now, why do I say that this is lossy? Because when you say it's blue, okay, it can have many shades of blues. If you use, for example, like only one shade of blue, so if it's light blue or dark blue, you use the same blue, okay, so you lost some of the information. But if you use like more, let's say you use like 4 shades of blues, okay, it's still not correct, okay, because the real one has infinite shade of blue, okay, so it's lossy in that sense. But this is how you compress the data and transmit to the digital communication system. Okay, so if it's black and white picture, you can use like brightness, okay, of the color. But if it's color picture, then you have to also send the color. The next technique is predictive coding, okay? This one, you predict the next sample value and send only enough bits to approximate the departure from the predicted value. What is this? Predictive coding. Okay, for example, if you want to send one, okay, if you want to send this number, and then send okay, suppose you want to send this, okay, this one and then this one and then this one and then this one. Okay, since the number is very large, okay, what is better is that you send this one first. You send one, okay, 1,200,123, and then the next one you send plus 1, and then this one you send plus what? 26, and then the next one you send minus 10. Okay, so instead of sending 1 million every time and have to send like many bits, okay, you can send the first value and then just tell the receiver that, okay, just +1 for the next one, and then +26, and then -10. This is good when the value is like high, but the difference is low. Okay. Then you want to sample at the minimum rate, okay, based on the range of frequency components, okay, in a signal needed to satisfy receiver eyes or ears. So if we are human, okay, we look at it, if this is good enough, okay, the picture is nice enough to look at, okay, we don't have to quantize more than that. Or if the sound, okay, if the sound is clear enough, okay, we don't have to quantize more. So we will use the bit, okay, as necessary. The next one is motion video. The motion video will send only the number of frames per second, okay, to look like continuous motion. So usually we have 30 frames per second, okay, so the frame is keep moving so that you send only the enough frame, okay, maybe 30 frames per second. And so human cannot detect, you know, human cannot detect, you know, with more accuracy. So if we can fool, okay, our sense, then it's okay. The techniques, okay, for the image, okay, compressed image is, we call it JPEG, okay, Joint Photographic Expert Group, okay, and we have for the movie, we have the MPEG, Moving Picture Expert Group,